Okay, so back again to do some examples using the concepts that we just discussed, or that I just talked about, regarding momentum and impulse. I have kind of some, I don't want to say basic examples, but they're not super complicated, but they're a good introduction to the kinds of problems that you're going to be working on um, once you're done watching this video. Um, so example one, this is just kind of getting the concept down to make sure that we're on the same page. We'll call this example one. Example one involves a situation where a ball bounces. Okay, so let's see. Let's actually make, so that's the ground. Okay, and we have one situation where a ball comes down and hits the ground with a velocity of 30 meters per second. When it hits the ground, it bounces back up with a velocity that is nearly the same as the one that it came down with. Comes up with a velocity of 28 meters per second. Okay. The other situation, maybe I'll do this in a different color. The ball, in this situation, comes down and hits the ground with a velocity of 10 meters per second. And when it hits the ground and bounces back up, it only comes back up with a velocity of 5 meters per second. Okay? And so, two different kinds of situations. I mean, before we get into the actual question here, let's think about what is kind of fundamentally different about these two collisions. In this collision, nearly all of the velocity that it comes in with, is there when it bounces back up. I mean, it's going in the opposite direction, of course, but the velocity before the bounce and after the bounce are nearly the same. Here, half of the velocity that it comes in with is kind of absorbed in a way in the process of that collision. So these seem to be two very different types of balls. And I think if you think about like a bowling ball, right? If you tried to bounce a bowling ball, it wouldn't really bounce very well. But if you have something like I don't know, like a tennis ball or a basketball, that'll bounce much better. Okay, so you can think of these two balls as being made of very different materials with very different properties. Okay, the situation here where most of the kind of velocity that it comes in with is conserved. Those kinds of situations, we call them elastic collisions. Okay, and elastic collisions are ones that I'll say conserve velocity, momentum. Yeah, they conserve velocity and momentum. Okay, and many of the situations that we look at are going to involve elastic collisions. Not every collision is elastic. Some are more like this, and we'll talk about those later on. Okay, but here the question is, which one of these has the greatest change in momentum from beginning to end? Well, let's see. In the situation with this ball, the total change in momentum goes from 30 meters per second to negative 28 meters per second. Again, one of them is negative to indicate that it's going in the opposite direction. Okay, total change in momentum here then, or I shouldn't say momentum here, because we don't know the mass of the ball. We do know the velocities though. So the total change in velocity here would be 58 meters per second. Okay, whereas in this situation, the change in velocity, I'm not going to write this down, I think you can just kind of see that it goes from a positive 10 to a negative 5. That total change in velocity is only 15 meters per second. So here, in this situation that is elastic, the change in velocity and thus the change in momentum is much greater. Okay, and that's something you typically see in elastic collisions. Elastic collisions tend to be involved with much greater changes in momentum and velocity. Okay, all right. Let's look at another kind of an example. This next example involves having to come to a quick stop when you're driving, and the context for this is like you're driving down the road and a deer runs out in front of you. Maybe some of you have been in this situation. I thankfully have never been in this situation, but it does happen where the car hits the deer and you come to a stop and the airbag is deployed and maybe you're wearing a seatbelt, and like what's the math and what's the physics behind that situation. So let's say there's a 50-kilogram person driving down the road at about 35 meters per second. So I think that's like maybe 40 miles per hour or something like that. Velocity equals 35 meters per second. Sees the deer, tries to stop, hits the deer, car comes to a stop, and a total time, or actually no, not the car, but because the person is wearing a seatbelt, and airbag is deployed, sort of like you could imagine if you're in that situation, you kind of suddenly move forward, and the restraint of the airbag and the restraint of the seatbelt brings your actual like head and body to a stop, right? So that whole process, because there's the seatbelt and an airbag, comes to a stop in, what's the time? Oh, 0.5 seconds. Okay, in a half of a second. Okay, and what we want to know is what's the average force, like what is the average force applied on this person. Okay, so what do we know? So in the beginning, so we'll say initial, the momentum is 50 times 35. Okay. 50 times 35 is something, I'll do these calculations later once I've got more things written down. The final momentum of the person is 0 because the person isn't moving at the end, right? So the change in momentum is the difference between 50 times 35 and 0. Do that calculation. 150, what is it, like 1600 or something? 50 times 35, 1750. Okay, so total momentum change equals 1750 kilogram meters per second. And change in momentum is equal to force times time, right? Change in momentum is equal to impulse. So to get the average force, we just have to take 1750 and divide it by the amount of time that it took to come to the stop, and then we get the average force. So 1750 divided by 0.5 is the same as 1750 times 2, 3,500 newtons. Okay, and that's a decent number of newtons. Yeah, I mean, let's see. What's we'll talk about the unit conversion from newtons to like pounds, so you get a sense of how a newton sort of compares to a more familiar unit, but that's the situation. Now, what's interesting and what's really instructive is if you're not wearing a seatbelt and you're only relying on the airbag, or there is no airbag and you're only relying on the dashboard, okay, what's the thing that changes? Well, everything stays the same mass, same velocity, same change in momentum. The big difference here is the time it takes to stop dramatically decreases. Okay, the whole point of the seatbelt is that it sort of makes that whole process of coming to a stop take a little bit more time. And if you're not wearing those things, then the time goes from something like 0.5 seconds to something more like 0.002 seconds. Okay, which doesn't seem like a big difference. We're talking about, you know, the difference of a snap and like, you know, it's not that much. But how does that impact the force? Well, if I take the same 1750 and divide that by 0.002 as the time, all of a sudden, as you can probably imagine, I've got an average force of 875,000 newtons. Okay, and that, I think, you don't even really need to have a good, clear understanding of what a newton is compared to a pound. 875,000 newtons is a lot. Okay, it's enough to make a big difference. So that's why seatbelts and airbags are so important. Okay, it increases the time of that change in momentum. All right. Okay, so that's enough about that. Let's talk about one more example. Okay, and for this example, you're going to have to use your imagination to help. I will draw a picture. Okay, so you could probably tell, because it's an amazing drawing, is that this is a picture of me on a skateboard holding a bowling ball. Perfect. Okay, so what's about to happen here? So I'm on the skateboard, here's the ground. Okay, we're going to assume that there's no friction. Okay, we're going to say that the mass of the bowling ball is, what did I say? 6 kilograms, about 12 pounds or something. The mass of me and the skateboard, me and the skateboard together is about 95 kilograms. Okay, and what I'm going to do is I'm going to throw this bowling ball at a velocity of 2 meters per second, and the question is what happens as a result? Well, so we're going to make some assumptions: no wind, no friction. The ground here is perfectly level, so we don't have to worry about that. Maybe you've been in a situation like this, or maybe you can imagine that if I am on that skateboard and I throw something heavy this way, well, immediately I'm going to be pushed back the other way because the momentum of this situation needs to, needs to be conserved. If it starts with 0 momentum, then the total combined momentum of me on the skateboard and the bowling ball separately needs to also be 0. Okay? This is kind of like those collisions, or I should say those explosions that we did and that we looked at yesterday with the carts, where the carts were together and then I hit that button and they kind of separated apart in opposite directions. This is just like that. Okay, so, yeah, what happens? What happens? So if I throw this bowling ball in that direction with a velocity of 2 meters per second for the bowling ball, the momentum equals 2 times 6, which is 12 kilogram meters per second. Okay? As soon as this happened, am going to kind of recoil in the opposite direction, and I have to have the momentum that's exactly the same as this. Okay? So my momentum has to be 12, which has to equal my velocity times my mass. Okay? It's kind of as simple as that. Okay, so if I take 12 divided by 95, then I'm going to get the velocity that I'm moving at in the opposite direction. 12 divided by 95, 0.13. Okay, so not super fast. Okay, but it's something, right? And you could guess that since I have a much larger mass than the bowling ball, that the effect of the change on my velocity is going to be smaller because I've got more mass, right? It's going to take more impulse to get me moving faster than the bowling ball, okay? So there are a few examples, okay? Those should be helpful. The notes that I gave in the first video should also be helpful. You got like 7 or 8 questions that I'm asking you to work on today, and I think that's it, all right? So I will see you later. Let me know if you have any questions. Cheers.